I come from a small 40-person startup in Palo Alto called Forward Networks, trying to bring intent-based networking to the world through network verification. And I'm really happy to see faces that I remember from 10 years ago in the very early days of SDN, both presenting and in the audience here. If you have any questions in the middle, feel free to interrupt me. I'm trying to keep this kind of short because I know that I stand between you and food. All right. And beer, that's even more. All right, so when people ask me, why does what we do matter? I think there's a nice way to explain it. And take a step back for a second. Networks are about connectivity, right? Okay, well, that's kind of obvious. Mother and apple pie. Networks are about connecting businesses to their customers. They're about connecting people to devices, devices to applications, applications to each other. They're about connecting people to people. It's 2019. On the way here, I passed a bunch of self-driving cars. Yet it's 2019 and we still have examples where networks go down. And that seems completely crazy to me. We read about it in the news occasionally, and it seems like the kind of thing that we should have a handle on. And so I want to talk a little bit more about why that has come to be and how we might change it with technology. So let's talk for a second about sources of network ops complexity, right? So if an outage occurs and it costs the business a few $100 million, we read about it in the news, the underlying reason is that the complexity in that network wasn't handled by a human, period. There's complexity and it wasn't managed. Either someone didn't find a way to remove it entirely or they didn't find a way to manage it. So here's something I want to kind of pitch to you, that the things that lead to businesses succeeding are actually things that necessarily lead to network ops complexity and are unavoidable. So we're going to have complexity, we're not going to be able to remove it, and I want to explain a few of the ways that arises first. So one thing is the businesses that succeed are the ones that hang around, the ones that grow by acquiring other companies, the ones that have existed long enough to have multiple generations of technology. So what does that lead to? Well, it leads to a few things. One is literal diversity in devices, different devices from different companies they've acquired, but it's not just that. It's also, even if the devices are the same in the companies they acquire, often the OSs may be different and the configurations may be completely different. And I say this having spent the last 5 years at a company that's going out to the companies of the world and trying to help them simplify their network operations. It's a surprising amount of diversity. Another thing, expansion to new regions. So yeah, that's of course going to lead to a much larger scale, but it also leads to even more of this device diversity, this device complexity, all the things that make networks much harder to manage. Multiple applications and services. So if you're a successful company, you're probably going to have a bunch of these. And the more of them that you have, the more frequently you're going to have to change that network. And continuing on, critical applications really lead to complexity. So a critical application is one where if it goes down, someone notices, right? And what application these days is something that's not critical, right? Everyone notices when a service goes down. We check down detector, or we go to Twitter, we find that those services are down, and we do something else, and we wonder what we're supposed to be doing right now, like if Slack goes down. What this leads to is uptime criticality, and this leads to operational complexity because enabling uptime necessarily adds complexity, right? It means additional devices, it means additional configurations for that purpose. So I'm gonna pitch the idea here that network ops complexity is an unavoidable result of being a successful business. It just happens that way. All right, so the challenge that modern companies have with, can everyone hear me? I don't have one of the mics.
For the recording.
Yeah, okay, for the recording, I'll stay up here then. All right, so the challenge of effective network operations, I'm going to break it down a little bit. So there's the in-the-weeds stuff, and this is from talking to operators and spending 5 years learning empathy for network operators. It's, you got to know what you have, you got to know how it's connected, and you got to know where traffic goes. If you don't have that basic understanding of what your network is doing, then it's going to be hard to do anything beyond that. Well, what is the stuff beyond it? Well, what that operator cares about is the network working, right? Yes or no, is it working? Okay, well, if it is working well? Is it working as well as I'd like? Not sure. And then the person above them, their boss, wants to know if the network is working. And all the way up the chain to the CEO, people need to know if the network is really working, period. And knowledge of whether that network is working is intent. So you've heard, who's heard of this buzzword intent-based networking? Gartner's trying to make it a thing. What does it mean? Well, there are a bunch of definitions. It's just like software-defined networking in the early days. To me, intent-based networking is any network where a high-level understanding of intent is something that drives network operations. In other words, an understanding of what the network is supposed to be doing is something that people can agree to and can directly lead to operations. One way it can lead to those network operations is if you describe your intent and then configurations are generated. So that's kind of the generative side or the configuration-oriented of intent-based networking. And the other side is the verification side. It's whatever network I have, is it working in the way that I expect? That could mean, are my 2 data centers connected with at least 2 paths at all times? Are the prod and the dev clusters isolated except through the ports that I've specified? Do I have a path from my database to my mid-tier servers to my web servers for my critical applications? A variety of ways that we can define intent as network connectivity or network isolation or fault tolerance properties. So let's say we know whether it's working. Well, what comes next? Where do we really want to be? Well, it's what do we need to change? How do we need to change it? And having confidence in every change that we want to do. So, intent-based networking is about making the things that you need to effectively operate much easier. But I want to, for a second here, use some real concrete numbers. So this comes from a real Fortune 500 enterprise network. This is our bread and butter. So the customers that we tend to interact with the most are large financials, they're large service providers, they're large enterprises that may do things like retail or media. And so this is for a real network where we reached out to all the devices, we collected the state, the configuration. I want to see a show of hands here, and we'll just keep your hand up if you believe there are at least this many lines of config and state in that network. And this is a network that has 12,768 devices. So pretty much everyone will believe it's at least 1 million, right? That's pretty easy. Okay, let's see 10 million. Who believes that there are 10 million lines? Okay, we have a few hands up. Does anyone think there are 100 million lines of config and state in that network? A few hands are up. Okay, who believes there's 1 billion lines of config and state? Anyone? That's a lot, right? Okay, a few people. All right, do we have 10 billion? All right, well, if you said 10 billion, it's a little over. So the actual number is 3,281,961,320 lines of text. So add up all the lines of configuration and all of the lines of text that you would need if you want to understand how this network is behaving to a level of precision to where you actually know where traffic is going to go, as in any packet from any port going in any direction. And it's not just that. This isn't a static 3 billion lines. This is hundreds of changes per week in this network. And what makes it even worse is the complexity inside it, not just the raw number of lines, but the number of different model and firmware combinations that we see in just this network. It's above 500. And this is a representative network. This level of complexity is pretty typical for all the networks we go to and all the things we see in practice, because of all those factors that made these businesses successful and caused them to exist over time. So I've got it printed out here at the bottom. Just summarizing, if you can't see, understand, or confidently act on network behavior, you're going to have network issues. And that's in 3 ways. The network is either down, and we hear about an outage, or if you don't hear about the outage, it's slow and becoming a problem for business, or it's stuck, and this is the one we don't hear about enough, where a company's ability to change their network is lacking to a level to where their competitors are starting to get ahead. And I've actually come across examples where they've had to delay new services because the network was in the way, and that led to them falling farther behind, including at internet service providers. So we think a fundamentally different approach is needed. And if you are a software person like me, looking at a problem like this where you have ginormous amounts of data that is in no way effectively managed, and that no human can manage without help, well, what do? Well, what did Google do 20 years ago? They added search, right? They added a search capability. If I want to know where a VLAN is, I should ask, show me this VLAN, and I should see all the relevant information that helps me understand where that thing lives in my network, how I access it, and how I change it. If I want to know about an IP address, I should know where that IP address is located, whether it's located in 2 places or 10 places or 1, and how traffic from that IP address can flow out, can flow in, can flow through. That should be a simple search away, and by simple search, I mean before I'm done typing my query, I should see the results coming back. They should be auto-completed. I shouldn't need any kind of manual. I should be able to just jump into this thing and have it work immediately. That's what it should be. So one of the things we've created is this ability for search. Think of it like Google for your network. It's fast, it's easy to use search, covers all possible network behaviors. All right, so that helps me understand what I've got, how it's connected, where traffic goes. But walking up the stack to the level of answering the question of, is it actually working right now, is what we call verify. And this is a way to take the intent for what should be connected in the network from a fault tolerance perspective, from an isolation perspective, from a connectivity perspective, and directly say, here's what I want, is that so? And as the network evolves, see if that's the case. And the right way to define these properties is not in terms of configuration, it's not in terms of topology, it has to be something that is in no way dependent on the network that you've built right now, but instead the network that you want at a higher level, more abstracted level. So this answers the question of, is my network working as expected? And it enables continuous validation of connectivity, security, and even some configuration sanity. All right, so you understand if the network is working as it should now. Now the question is, you're looking to do a change. And so predict is about, will this change work? And the best example I have is someone looking to make an ACL change. So the first question I have is, well, if I make this change, is it going to do anything, right? Is this going to do anything at all, yes or no? And if it's going to do something, is it going to do the right thing? Is it going to remove or add the connectivity that I expect? But it doesn't end there. So a software viewpoint kind of affects everything that we do and how we think about using models to drive networking. So in a software context, if I'm writing a patch, and I do this on a daily basis, I have a patch of code, I'm looking to deploy that to production, I need to know what that's going to break. So I write a test, I make sure that's actually improving the thing that I'm trying to improve, but then automatically I have systems that will help run all of the tests that have ever been built for this software product to make sure that I'm not regressing in any critical areas, right? That I'm not breaking anything unintentionally. And the more tests I have, the more confidence I have that I can evolve the system rapidly. It's almost a no-brainer. But networks have never had that ability to do regression testing. And so what Predict helps you do, especially for things like ACL changes, is answer, well, are any applications going to break as a result? And then, even beyond that, if I make my change, am I done? Are there other firewalls down the line where my traffic is going to go to that also need a change, or are there other network changes that need this as well? All right, so how does this work, right? That's the next natural question. I want to describe how our particular product works. So we go out to network infrastructure. We talk to all of the switches, the routers, the firewalls, the load balancers, as well as both the physical and virtual versions of those devices increasingly. On top of the network infrastructure, we reach out and grab all the config and state through whatever possible means we have. And right now, the least common denominator is SSH, and there are a few more optimized means. So BMP, BGP monitoring protocol is one way that makes it a lot easier to get giant routing tables out of devices. There are a few other protocols that are coming out for that. Whatever means necessary, we go out to the devices, we grab all the data they've got, and we build a vendor-agnostic abstraction. So this kind of looks like an open flow view of the world. Every network device can be represented as a set of tables with links between those tables and forwarding rules that connect those tables. And then between these groups of tables, you've also got links. Every network we've ever seen looks kind of like this. On top of that vendor-agnostic abstraction of rules and links, we run an algorithm called header space analysis. And one of our founders, Payman Kazemian, as part of his PhD thesis at Stanford, created the world's first algebra for networking that would scale to interestingly large networks. And at the time, we thought, this is amazing, this thing is ready to deploy. And then 5 years later, after a lot of work, it finally was actually ready to deploy. It worked on one network. This was back in, say, 2011, 2012. It showed that this was all possible to represent all networks in a consistent way. But that didn't mean that the information was instantly accessible. It didn't mean you could, as a human, write checks that you could understand easily. It didn't mean that the information you got back when you did a search was something that every network operator could understand, or that it was it was using the terms that network operator would really get. And so over the last 5 years, it's very much been about addressing these three issues of figuring out how the world's network devices behave individually and together, period. And that's pretty hard. You've got to build a lot of infrastructure for that. Scaling it to the level of 10,000 plus network devices on a single instance. And then finally creating an interface that doesn't require a manual, where people who are junior network engineers understand the concepts well enough to understand what data is being presented and then what to do with it. And quickly we learned you have to connect the data all the way back to the lines of config and state that you're using for your model, that people wouldn't trust it necessarily. Oh no, my network can't have that behavior. And then the light bulb turns on and they understand this thing that's been obscured from them for a long time. All right, so on top of the header space analysis, on top of our behavioral database of the network, or think of it as a digital twin of your network, we have a REST API layer. We build in some applications. I've mentioned search, verify, and predict. We also have a means of doing diffs at a behavioral level, so it's not just what text has changed, it's how has my network behavior changed, what are the VLANs that have changed, what are the routing rules that have changed, what is the traffic that is now taking a different path. And in addition, we've got the ability for users to add their own capabilities through this same API. Now, this can be as simple as anytime my network changes, I want to update my snapshot and test that the network is behaving as it should. We have both greenfield and brownfield deployments that are doing that kind of thing. But there's some more interesting integrations I want to talk about briefly. So one of them is at a payment processor that wanted to give anyone in their company the ability to ask, is the network transmitting traffic in the way that I expect? So should I expect connectivity or not? And if I shouldn't expect connectivity, then maybe raise a trouble ticket, but if I should, maybe tell them, oh yeah, here's what I'm expecting. So kind of initial triage through Slack, through a little chat bot. And that was something they integrated on top of the API. Another example is an application-specific view of a network. So imagine I'm trying to debug a specific application. I don't care about 99.5% of the network that my traffic's not flowing over. I only care about the 0.5% in this particular case that my traffic is actually flowing over. Those are the devices that I want to see the counters on. Those are the ones where I want to see if they're reaching any resource limits. Those are the ones where I want to know how many path choices I have that may be affecting my application behavior. And so this was a customer that had combined data from Sev1, which does counters, Forward, which does paths, merged them into a custom view. They did this in nights and weekends in a little Go application, and they were able to make it real easy to type in an application with some IPs and then see a custom debug view of their entire network. What's really cool about this is, despite the underlying sophistication of what you get, the deployment process is really easy. So you can deploy it on premises or in the cloud. It's really plug and play. So you run software, either a little bit of code that you install locally that only requires a few gigs of RAM, or you run a full VM that's doing all the processing. So we've got these cloud and on-prem options. There are no agents to install, right? We're connecting out devices in the same way humans do, so there's nothing else to install there. And we're read-only in terms of the credentials we need, so there's no risk to the network. It's only value in terms of pulling in and understanding information. And there's no real need for a workflow change here. There's access to information. There's the ability to add that information into trouble tickets. But you don't have to change. We're not forcing anyone to learn a language, to implement their network in a particular way. It's the entire network that we can pull in and give value on. So pretty quickly, I want to talk a little bit about some use cases and what's driving adoption of a technology that I'm here because I believe is transformative to networking. All right, that's how we factor into Network Transformation Congress. So network behavior analysis, these are, I want to, at the front of a trouble ticket, see where the traffic is, where it's going, and whether that matches my expectation. I'm trying to triage an issue that's taking a while, or more interestingly, for security or applications people, making network behavior something that they're aware of. So we worked with a payment processor, a different one, who wanted to make sure that every time every one of their applications on the main payment processing cluster changed, that the network connectivity they needed was there for that application deployment. Because if it wasn't there, they shouldn't be wasting their time, right? And that was just a waste of everyone's time on both sides. So they built an API, they built an interface by which their application developers could ask the network, is it providing the connectivity that I expect? And that completely changed the number of trouble tickets they had to handle, where they would say, yep, it looks good. That kind of thing. Second example, so second from the left here, network documentation and visualization. I thought this one was so simple, so basic, and yet this is where a lot of the value is, that a lot of companies don't know exactly what they've got or how it's connected. And just having an updated live map that they don't have to worry about, that isn't Visio and isn't obsolete the moment that they save it, has a lot of value. A third use case I want to talk about is post-change verification. So I have been on a call it was a Saturday night, and they were East Coast time, and I was Pacific, so it was even later for them. They had been up 16 hours, and you could kind of hear the bleariness in their eyes, because they were starting to slur their words a little bit, and this is a network operator at a bank who just wanted to go home to their family. But their job was on the line if they didn't do a great job, and on Monday morning, the trading floor didn't come up. So they were pleading, tell me how my network is working, tell me that I can go home, give me any confidence you can that the changes that I've made are safe and that the network is in a good working place. Anything you can do there to speed up or improve the quality of post-change verification matters tremendously. And we're doing all kinds of features to make that process much faster and much easier to use. And then this fourth option comes from a bank as well that the use case is from the ROI sample in the middle. They want to do config and network audits. And so they found that an investment of about $600,000 to cover a majority of their devices, they expected, these are numbers from them, not from us, they projected would save $3 million a year. And this is because they found that they could reduce the number of what they called self-identified audit items, so items that they found that they believe are worth fixing in their network. And these are typically a manually found sort of thing. They thought it would reduce the number of audit tasks, that it would speed up the time to fix these, as well as, and this is pretty important, remove about 1/3 of aborted change windows. So that's 1/3 of Saturdays they don't have to repeat, which is pretty cool. And if we zoom out a bit, it's what is all this about? What are the use cases for a mathematical network model? Well, on the right side here, it enables a de-risking, and very few technologies in networking have really enabled de-risking in the past. A lot of it's faster, it's easier, it's a little simpler, but very few are enabling de-risking of operations. And the usual things like improving OpEx and agility and reliability. All right, so I want to encourage you to come by our booth on that other side. I'd be happy to give you a personal demo. We're going to be here tomorrow as well. This is the kind of thing that you have to see with your eyes to really grok because it is so different. And this is a picture of a network where we started out with a list of devices, a list of credentials. We go out, we grab all that, build a map of it, we massage the picture a little bit. And this is our demo network that I want to point out because it includes at the top elements from an Amazon VPC, at the bottom elements from NSX, in the middle an MPLS transit network, as well as all kinds of more traditional networking devices, things like Cisco ASAs, Junos, Palo Alto firewalls, F5s, Arista devices. This is a smorgasbord, and this is a tiny one. This is only 120 devices compared to the 10,000 plus that we're used to seeing. But I highly encourage you to come by and see what search is like, see what verify is like, see what the diffs capability is with your very eyes. All right, so I prefer showing rather than telling. But I want to point out this slide because in the right side here we've got some, what was that? I prefer to show rather than tell. And this is an example of telling. So this is what not to do in a presentation, but here's the reason I'm showing you this. I'm showing you, I'm telling you that we're getting validation from the industry and customers because I believe that we're now at a time where the industry is starting to realize the value of a mathematical network model and how that really can change the way that companies do network operations. Right? We're starting to see it because we're getting more press, because we're getting some of these awards. And I want to point out the top right. So Gartner does this thing called verified reviews. And to post it's like Yelp, except they make sure that you are who you say you are and that you work at a company that's actually bought the vendor's product. We're very happy that it's all 5 stars around because we focus on the user experience and the short description of what we're doing. And I love it. I couldn't have written a better one. Is it's a brutal problem they're solving, and they're doing a great job with it. I mean, if there's anything I've learned in the last 5 years, it's empathy for network operators because it is a brutal problem, right? Complexity, you can't just wave a wand and 10 years of embedded network complexity and diversity goes away. We're working on things that are going to make that much better, but there's still a need to manage what is there. And so to kind of get back to the question of the talk, does intent-based networking need a greenfield? Absolutely not. In fact, the greatest value is on the brownfield side. But we actually have production deployments on the greenfield as well. It can help kind of bridge the gap in the testing between those two. All right. Would love to offer a trial to any company here that wants to try this out for 90 days. Plenty of people to talk to behind the booth. All right. Any questions? Thank you.
Not really a question, but a comment. This is the coolest thing I have seen in a long, long time.
Oh, thank you. I did not pay him.
So you've mentioned a lot of devices that have either IP addresses or MAC addresses. But one of the challenges is correlating what happens at the optical layer. So can you handle the optical devices as well that might not have IP addresses or MAC addresses?
By the way, Dan, you mean the physical layer frame?
Yes.
So we don't handle optical devices at the moment. And the reason is we wanted to target the chunk of networking that would give us the greatest coverage. And the reason is when you go into a network, you don't just want to do 50%. Network modeling doesn't provide a lot of value if you've got giant blind spots in the same way that a self-driving car that can't see its own blind spot is going to have real issues. So we need to get 99+% coverage to have viable mathematical network modeling where those little gaps don't get in the way of your ability to verify or do searches. So we wanted to focus on the devices that are the most widely deployed. I think optics could come later. Some of the campus-oriented, especially wireless stuff, I think would come later. Some of the more virtualized stuff, like I'd say Kubernetes and containerized networks, is going to come later, probably sooner than we think.
So one follow-up question. You're gathering a lot of data on the state of the network and its expected behaviors. You've coded it in a certain way with your model. This seems like an ideal candidate to apply machine learning to and do some predictive analysis. What are you doing about that?
Yeah, so the data we're collecting is highly, highly structured. It's not text that has all kinds of issues with cleaning it and naturally lends itself well to more statistical or machine learning oriented approaches. So, at this point, we don't need machine learning. We need an understanding of what the network is doing. And the most precise way we have is header space analysis that tells us exactly where those packets can go, how they're going to get split, how they're going to get transformed, and where they're going to go. But looking forward, if you've got all this data from a lot of the world's networks, and you've got individual deployments that are applying this analysis at scale in a centralized location, you can start to imagine learning from those deployments. Right? Starting to identify common patterns, potentially building classifiers that could say, in the past, we've seen that this kind of network that matches these, like if you squint, it looks like this, is more likely to have this kind of issue. I think that gets very interesting, but we're not there yet.
That's it.
Brendan, hi. A very nice talk. And we spoke a few years back at one of the events in the Valley. I forget which one, when you were just a couple of years into this. And it's very nice to see where it's come and the clarity with which you just explained it. So that's great.
Thank you.
One question I had is when you're looking at a network with like 12,000 plus devices, which is even only a part of their network, you have a lot of bad data in the sense that sometimes you might not even know that the device exists. And where do you get the information to pull the stuff off of the devices? Because sometimes the situation is so bad at a large operator or even a large enterprise that they have stranded devices. They don't know that they exist. They don't know that they bought capacity, stuff like that. So how do you guys handle that?
This was the greatest surprise for me. You go to some of the best run networks in the world and they don't know what they have.
Yes.
And you scratch your head and you go, how is it possible to keep this thing running? And the answer is if you have that many devices, it's easy to have one fall in a closet and no one ever notices it. So the way that we discover devices is typically with an initial import through, say, CSV or through JSON API. You seed it typically with a configuration management database. Most people have that and can export the data.
Sure.
We try to find all those devices. We try to optimize that process of seeing if the devices are there, and if they're not, give you as much detail as possible. That's something we've really worked on lately to make that process quick and easy. Once you've got that initial set of devices, then we can start to discover the links between them through things like CDP and LDP, as well as some table matching, MAC kinds of learning approaches that aren't LDP or CDP, but are trying to fill in the gaps automatically. You can add links manually if you want, and we can suggest neighboring devices that, using heuristics, seem like something you probably want to connect to, but at all points, the user has to be in control, and we don't want to start hacking your neighbors.
Right.
So we'll provide a list of suggested neighbors, and you can click a button and say, yep, all these look reasonable. Let's go ahead and let's see if the credentials we have enable us to connect to those devices and add them into our model. Cool. So there's an initial phase of getting a clean model that covers everything you need. It takes a little bit of time in the beginning.
Sure.
But we've tried to make that process as easy as possible, because once you get past that step, you now have value. You now can search in your network. You can find things. You can do the world's best trace route. You can start to verify properties. You can triage problems that you had no visibility into before.
Exactly. And then in this process, have you guys discovered that there are situations, maybe more than one would like, where the people are like, oops, we didn't know we had something in this CO or in this part of our network? Do you find that comes up more frequently than you'd imagine?
All the time. Every single network we've ever gone to has had some kind of misconfiguration. And that's not that we go to bad networks, it's we go to some good ones.
That's just,
and
as you said,
it's
that's
just
the
hard
way
to
it
manage
is.
at a certain scale.
All right, thanks.
All right, last question, then beer.
Okay, Christos.
Can you please elaborate a little bit of how did you guys verify the correctness of your mathematical models? Did you also have to run simulations, or? And a follow-up question is there any embedded like self-learning in these models, or because I'm assuming you're collecting the data right from different networks, and do you use these to improve your models, or is there any evolution involved?
It's a great question. We do everything we can. So we have 6 racks in Santa Clara of millions of dollars of networking equipment that we're continually pushing configurations to. Hundreds of configurations for every device. For every device, it's every OS. For every OS, it's every firmware version, because you can have firmware versions that change behavior in significant ways that we need to model. We need to iterate through all of those very quickly. So we've built custom infrastructure to change between versions automatically, to figure out what tests we need to run. We're at a point where we have over 100,000 tests that we want to run every time our software has even the smallest change. So if that's the state that you're at, you need to be smart about what tests you're actually running. And so a lot of what makes this whole product concept possible is infrastructure automation. A lot of people don't realize this, but this is the grind you need to go through to support. We're on the order of about 30 different OSs at this point that we support, and that's the number you need to support a majority of what's out there. So it's not just that we're writing human tests and we're seeding it with what we call unit packet tests. So it's where a test where we know what the output should be, we know where the packet's going to go, and we've generated the input. It's also when we build a model, we test whether every path that model predicts is valid. So think of it as you start with your test, you know exactly what the behavior should be. You confirm that you understand the behavior given a configuration. And then once you're at that level, you've maybe covered 1%, 0.5%, 10% of a device, it really depends. You want to get the rest of that coverage through automatic means. So we do that. And then once you're past that, if you want to increase the rate at which you find bugs in the field, you've got to start adding things like assertions. So there's a lot of custom infrastructure to know that the model that we provide is correct, because given a configuration of a device and its state outputs, you've got to get it right? Think of it like we're building offline models. We're testing them with all the configurations we can possibly think of. And there's even some stuff beyond what I've described that's trade secret protected at this point.
Have you discovered any of these models to break after you actually test out with real data, or it's been pretty consistent?
So we've gotten vastly better with time, right? As if you have 3 people who have the same device, they're probably going to exercise most of the features there. So what we find in practice is the most likely reason for missing something is if there's a feature that potentially one customer has ever used from Cisco. And there's one example where a service provider's config matched the manual's description of that feature, which tells me that they're the only user of that feature in the world. And so necessarily, unless we cover every feature that ever has existed first, which would take infinitely long, then we couldn't handle them the first time. So we even have features to understand if we've ever seen something. So it's, do we know what we don't know? What are the new features we've never seen? And then to shorten the cycle, which is unavoidable, of adding support for that on real devices and then bootstrapping the support. So a lot of it is just how do you get support for devices very quickly? Good question. Thank you.